This video introduces context-free grammars. I'll start off by talking about hierarchical structure trees, which provide the background intuition for context-free grammars. Then I'll cover constituencies and dependents, followed by a case example of drawing a constituent tree for a sentence. I'll finish by discussing grammatical correctness and a phenomenon called center embedding. In many languages, including English, sentences form a hierarchy with individual constituents being grouped into progressively more general classes. A sentence's structure defines the dependencies between constituents within these hierarchies. These hierarchies are often modeled using trees. Hierarchical structure trees usually have both internal nodes that specify structural properties like constituent or part of speech type, and external or terminal leaves that specify surface word forms. These nodes and leaves are connected to one another by branches. This results in something that looks like this, where the root node signifies the entire sentence, and then as you move deeper into the tree, the sentence is broken down into progressively smaller parts until every word is accounted for as a leaf node. These trees can quickly grow to be highly complex, but that's part of the reason why hierarchical structure trees are useful. They can take complex sentences and break them down into simpler subtrees, facilitating more effective language processing. The grammars that define these hierarchical trees are referred to as context-free grammars. Context-free grammars, or CFGs, are mathematical systems for modeling constituent structure in natural language. A lot of times you'll also hear them referred to as phrase structure grammars. CFGs can describe all languages that can be modeled using finite state models or regular expressions. The term context-free stems from the fact that a given subtree within the tree can be replaced with some other subtree that matches the structural constraints, independent of the other nodes in the hierarchy. The rules governing which strings a CFG can generate are called productions, and productions can be hierarchically embedded. So you might have a production rule like the one shown here, where a noun phrase can be decomposed into a determiner followed by a nominal, and a nominal can be further decomposed into a noun or a nominal followed by a noun. Production rules thus determine how constituents can be combined with one another, and a constituent just refers to any group of words in a CFG that can behave as a single unit. So constituents might be things like noun phrases, prepositional phrases, or verb phrases. Phrases like these contain both heads and dependents. Heads are the main words governing the constituent, so they can generally stand on their own to at least some extent, whereas dependents are the words providing additional clarifying support, so they can't stand on their own, but they do provide meaningful content to the phrase. Dependents can also be either arguments or adjuncts. If they're arguments, they're obligatory to the phrase as a whole. If you remove the argument, the phrase no longer makes sense. If they're adjuncts, they're optional. If you remove the adjunct, some of the meaning might change, but the phrase still makes sense. In general, constituents can be substituted with one another in the context of the greater sentence, and they can also be moved around within the context of the sentence. They can also be used to answer questions about the sentence, making constituency parsing useful for things like question answering systems. The way that constituents are structured in a tree corresponds to their meaning. So we can take two very similar sentences like you see here. I ate spaghetti with meatballs and I ate spaghetti with chopsticks. Even though we're only substituting one word, the meaning is actually quite different. In one case, we're talking about spaghetti that contains meatballs, and in the other, we're talking about eating spaghetti using chopsticks. We can try out drawing a constituency tree for one of the phrases from our last video, time flies like an arrow. We'll confine ourselves to the production rules you see here. So we have a few different ways to specify noun phrases, a few different ways to specify verb phrases, a few different ways to specify prepositional phrases, and then the words that match the base part of speech labels of preposition, verb, determiner, and noun. So we'll start out and we'll just check to see which parts of speech we have here. If you're watching these videos out of order and you're curious how we got these part of speech tags, I'd recommend watching the previous video on statistical part of speech tagging. So we have a noun, verb, preposition, determiner, and another noun. Now, it looks like there's only one top-level production rule, so we'll go with that, and we'll end up branching down to a noun phrase and a verb phrase. Now, there are a few different production rules for noun phrases. We'll go ahead and select the middle one. There are also a few different production rules for verb phrases, and we'll select the first one. Now, based on our production rules, it looks like with the noun, we're ready to branch down to a leaf node. We'll branch down to a verb from our verb phrase, and down to a preposition and a noun phrase from our prepositional phrase. Now, from the verb, we'll branch down to the word flies, and from the preposition, we'll branch down to the word like. We'll decompose the noun phrase further into a determiner and noun. And finally, we'll end up with a leaf node for an and a leaf node for arrow. Now, I had some professor senses telling me which production rules to choose in this case example, but in next week's module, we'll learn how to programmatically build hierarchical structure trees. So now that we've worked through a case example, we can quickly look at the formal definition for a CFG. A CFG consists of a set of non-terminal nodes N, where N contains all of the allowable constituent types in your grammar. A set of terminal nodes sigma, where sigma contains the allowable vocabulary words in your grammar. A set of rules R, and a start symbol S, which is a member of N. We say that a sentence is grammatically correct when the CFG can construct a valid hierarchical structure tree for it, meaning that all the words in the sentence are reachable as terminal leaves. Now, this includes really complex sentences. For example, I can say, Natalie knew a lot, kind of a little brag moment here, and that's a really nice and easily interpretable sentence. I can say, the zebra that Natalie knew a lot, and that's a bit weirder, but still okay. Or I can say, the unicorn that the zebra that Natalie knew a lot, and that's like a mind-blowingly confusing sentence. However, formally, it's still grammatical. Issues like this happen because of a phenomenon called center embedding, where we end up with these recursive rules in CFGs. So technically, the last sentence from the previous slide could just go on getting weirder and weirder for as long as we wanted. Very few humans would consider the last sentence from the previous slide to be grammatically correct, though. So we found one failure of CFGs, which is that they're unable to capture bounded recursion. It'd be great if we could specify something like, you can only recurse upon this rule one time, but we can't. Because of this, linguists acknowledge that formal grammaticality isn't exactly the same as the human perception of grammaticality, because the human perception of grammaticality also takes processing and memory limitations into account. However, CFGs are still a very useful way to model language, and in the context of this class, we'll just make the simplifying assumption that if something is accepted by a CFG, it's grammatically correct.